So good afternoon, everyone. Yeah, so as I said yesterday, I'm hoping to set these lectures in a relatively self-contained way. So this was the final product of yesterday. It was we derived some relation starting from conformal field theory crossing equation and integrating it against some. This was the basic argument here was based on integrating against some. So we took some expectation value of some field and we integrated field in some null direction, phi dx minus phi. So there was this argument that this commutator should vanish when these two fields are on the same null sheet. And by manipulating this commutator, we wrote it in terms of a different commutator square and got some rules that map to something like this. And so what I want to do today is three things. So I want to explain how to use this thing, which is not entirely obvious because the only thing we know here, so maybe I can also draw another picture. So the picture is that this thing, we derive it from CFT, but the sort of CFT constraint are supposed to be a superset of the S matrix constraint. That will be the subject of today. And okay, there may be a little bit of overlap. It's not there's some technical details here that remain to be fully worked out. But roughly speaking, the picture that we argued yesterday is that every time you make a S matrix sum rule, it uplifts to a CFT sum rule, at least in some flat space limit. And the S matrix picture for how this is supposed to work is if you imagine the complex S plane, what we're doing here is that we're doing a contour integral where we have a contour that looks like this. And we pick a scale m square that is going to determine that the scale at which our EFT is valid. And then you have some I energy on the other side. And this thing was supposed to come from saying that the integral over this contour, the contour can be deformed to infinity, gives you 0, therefore you get a relation between the integral of the imaginary part at high energies to something you can calculate at low energy. Okay? So this gives constraints on effective theories. And we've not quite explained how to use it. And part of the reason for why it's not obvious is that the only thing we know about high energies is symmetries. We're assuming that we have rotational symmetries, so we can do a partial wave decomposition. And from unitarity, the unknown coefficients in this expansion are bounded, and they're positive. But that's all we know. We know that these unknowns are positive. But this Lejeune function itself is it's like a cosine. It's oscillatory. So we're taking these positive unknowns and multiplying by things which can have any sign. So at face value, we still have to work a little bit to get some information out of this.
So can you remind me possible where the positivity comes from?
The positivity of that?
Yeah.
Yeah. So in the CFT side, it came because we got this phase factor that gave us this 2 sine square. In the S matrix case,
S matrix is clear.
Yeah.
CFT side.
Yeah, that was that. Yeah, exactly. So each commutator gave us a factor of sine, and commutator square gives sine square, which is great.
Sine square multiplying something that you already knew was positive.
Also, yes.
And that was
The OP coefficient square are positive by unitarity. Great, thanks. Exactly. And now everything that went to the block went to do this Lejeune function. So the only thing that with sign is not clear is this Lejeune function. Yeah. So I will try to explain how to actually use it to get something, and this will be a little bit brief. Part of this, it would overlap with one of my lectures last week at the school in Bhopal, but I would take a slightly different angles actually in order to take some shortcuts and the less historical route. Then I also want to say a few words about how to think about this equation directly in the S matrix case without deriving it from CFT. I want to make contacts with things like bound of chaos and so on that other people have thinking about. And well, hopefully I will get to say a few words about gravity. Good. Okay. All right. Let's see. So I'm wondering if I should start by saying a little bit. Maybe I can start by maybe the first thing I could say is stating what the conclusion would look like for gravity. So let me start with the conclusion, and then we can think about it through to the lecture. So one of the slogans that sort of picture that we want to elaborate on is the following. So the message will be that in any theory, theory that that preserves unitarity. So probabilities are positive, basic rules of quantum mechanics, plus causality in the sense that you cannot send signal faster than light, and has some light spin 2 particle. Or excitation. Any such a theory, there will be an important scale. There exists a scale, which I will call the scale of I spin onset. Let's call it basically, which is such that at lengths length scale less than this set by this energy scale, the basic framework of gravity plus coupled to a QFT must break down. And on the other end, at length scales longer than this scale, gravity coupled to QFT must work. Okay? So I want to advocate for this notion that in any theory of gravity, there's a unique scale. In string theory, that could be the string scale, or it could also be the Planck scale or some higher dimensional Planck scale. Whichever is the smallest of these scales will be that higher spin onset scale. So I want to advocate for this notion. Some of these, at least part of the statement that the theory must break down when you start getting these higher spins is something that is demonstrated in, at least to some extent, but we can always try to make the argument and proof more general, which I think there's a lot of room there to improvement. The statement that EFT must work in this region is also demonstrated in some cases. For example, the graviton 2-to-2 scattering amplitude must coincide with the one computed from effective theory. So we can prove simple statements about some amplitudes, but that's not like yet the full general statement we would like to have.
So suppose the way the first statement could have failed is that you have, let's say, a higher spin particle, and then there is a large hierarchical separation until
the other ones, yeah, exactly, yeah.
So it basically says that once you have this higher spin particle, all of this.
You're doomed.
You're doomed.
Yeah. Well, yeah. The concept that, so at low energy, this is something that, like the framework of gravity plus quantum field theory is a very strong framework. It's basically effective theory, right? You take the Einstein-Hilbert action, you imagine that the metric is not fluctuating a lot, which is at long distances, it's not. And you couple it to a QFT of your choice. Yeah, there's a question.
Yeah, if I'm agnostic about this high spin, and if I scatter two graviton, how will I see that there's something going wrong?
Yeah, this is exactly the scale at which the graviton amplitude will become modified. So basically, you'll be forced to produce these guys in graviton scattering.
And those guys may be 2 gravitons.
No, the amplitude for 2 gravitons would be too small, unless you're the Planck scale where that would be those. Yeah.
But say we were in ring theory, it's basically the scale where the loops are becoming important, right?
Yeah.
So 2, 3, 4 gravitons.
Yeah, you could say that. Yeah, exactly. Yeah. But yeah. So it's either a single particle, elementary particle, like a string state, or if you don't have some string scenario, you have a Planck scale. Then okay, you could call it loops, but yeah, everything breaks down then, so we don't know what we're doing anymore.
Is Nargen used in this thing? Not yet.
Yeah, so yeah, let me comment on how this relates to this large N paradigm. So in CFT, this criterion here is very much inspired from to this HPPS paradox, criterion. So Emskir, Poczynski, Pernanes, Suli, about I think in 2009, they made this proposal that any theory with a large N expansion and a large gap, meaning that few operators with twist less than some large gap number should be described by Einstein gravity. Should be Einstein. Great. So that was their. This is great. Oh no.
If you press somewhere else, it might go. No, if you press the button somewhere else.
Sorry, I made it worse. I was just checking.
Okay. Oh. It's not gonna come. Okay. Okay. So this is a notion. So yeah, what we're doing is a little bit related, but we want to go beyond in some ways. Yes.
Yeah. So what happened at exact equality in the first state?
Let's see. I guess at the threshold it's probably breaking down.
Okay.
Yeah.
And the second statement is for holographic CFT or any CFT?
Yeah, so the idea is that the main idea of HPPS was to identify what is holographic CFT.
Okay.
So the idea was that these two principles were a definition of holographic CFT, and you have a large N and a few operators that are light, and this is definitely an inspiration for this criterion. So for example, instead of large N here, we'll be effectively putting that the TT two-point function is large. And using that, which is the same as saying that the graviton amplitude, because the graviton amplitude is T divided, is the amplitude of T divided by this normalization is small. So it's the same as saying that it's the same as saying that the graviton amplitude is small. G Newton equals small. So in units of the, in this context, the units of the AdS radius. So essentially, we only have to assume that, and using this assumption, we'll show that this amplitude is small, and that's going to be the analog of large N factorization, at least for the graviton scattering. So we don't have to assume large N factorization separately; just the largeness of this number would be enough. On the other hand, we also don't want to assume that matter is weakly coupled. So we allow the QFT to self-interact strongly. Right. So for example, you could imagine a scenario where we have something like a Yang-Mills theory in AdS4, and it hits the confinement scale at somewhere the confinement length is sub-AdS radius, so it confined. So you have strong interactions in the bulk. We want to allow this sort of scenario. We don't want to think of 1/n as a universal perturbative parameter that makes everything perturbative. The QFT itself could be strongly interacting, but the coupling between it and gravity is weak, because imagine that in this regime, gravity does not fluctuate a lot. Okay? And effectively, all we need in this coupling are the expectation value of stress tensor of the QFT. So if you know all the expectation value of stress tensor of the QFT around the vacuum, you can see how gravity reacts to this coupling.
But you can have a higher spin hadron.
Yes. So this I-spin onset, very good question. So the question is about, so this I-spin onset is not going to be about the existence of a higher spin particle.
Okay.
So there are definitely states of the hydrogen atom that have spin 4. And we don't think that they make space-time breakdown. and the specific reason is that is going to be, this onset is going to be characterized by, is going to be probed by graviton-graviton scattering. And what happens is that this has to be this higher spin particle. Effectively, it has to be a particle, we only care about particles that couple strongly to two gravitons. So specifically, it will be a statement about the spectral density for spin 4 coupling of graviton-graviton goes to anything. Okay? Yeah, anything, yeah. Anything with spin 4. Okay? And essentially, as soon as you have a particle with strongly coupled to two gravitons with, with a state of spin 4 that's coupled strongly to gravity, this will signal the onset of the breakdown of space-time as we know it. Okay? So that's the picture. But yeah, so we don't care about any spin 4 state, but just specifically those that couple strongly to two gravitons. So for example, in string theory, the string state has a coupling here that's proportional to square root of g Newton. On the other hand, if you take something like hydrogen state, or an electron or two-particle state, it will couple to two gravitons which instead of being 1 over a single power of 1 over m Planck, it have a coupling that is 1 over m Planck square. So yeah, this could be a matter, plus minus or whatever. So if you look at the probability of scattering two graviton and making a composite state of particles, is way too small to matter for these arguments. Okay. So that's the picture of the world we try to support by thinking about the tough experiments involving gravitons.
So just to reiterate, what you will be showing,
Uh-huh.
what
Yes.
you want to show is that in the CFT language,
Uh-huh.
TT, can you say that?
Yeah, yeah.
In the CFT language?
Yeah, in the CFT language, we'll show that once you have this situation, this implies that TTTT must match. Once you have that and this notion of a small spectral density in spin 4, it will imply that TTTT is exactly as computed by Witten diagrams and for Einstein gravity. So that's the positive result in this direction. And there will also be a positive region, a positive statement in the other direction in terms of loops that we can calculate. If you model the matter from some one loop approximation, we can make some statement in the other direction.
The energy is much below both string scale and Planck scale. Theory has to be classical Einstein gravity. Scattering has to be classical Einstein gravity.
If the energy is much larger?
Much below.
Below, yes. Yeah. I try to phrase it in terms of length because I think energy is sometimes misleading in this situation. You know, like the Earth has a big center of mass energy, which is much bigger than the Planck energy. Exactly. But when we're scattering the Earth around the sun, we're not actually probing short distances. So it's better to think of the cutoff in terms of distances that you're probing.
Can you tell about the second statement with plus few operators with tau less than tau m? How it is related to Einstein gravity?
Yeah, the way they motivated it is, first of all, they observed that it's always true in all the top-down models. Because when you crank up the string scale in models of, say, for example, in AdS 5 cross S5, you have two scales that are important. There's a Planck scale in the bulk and the string scale. And when you crank both of these to high energies, all you're left with are the massless states. But we're also, the other thing we allow that's important, and that was a little bit obscure in their method, is that we also allow for towers of spin 2 particles. So that's the other thing you have in this AdS 5 cross S5 scenario. You actually have an infinite number of spin 2 particles that don't quite become light. They have the AdS scale. We allow spin 2 KK modes. We allow this type of things. Okay? But we don't allow higher spin exotics to be light. Yeah?
You mentioned the comment that if you are scattering below this Planck or string length, it should be gravity, but if there is a warp space-time, won't warp space-time introduce its own characteristic length which might change.
Yes.
Two-gravity.
Yeah, I think if you have some compactification and so on, yeah, so we're definitely not at this level of refinement. There's definitely some notion that you should think about the higher dimensional length scale in Einstein frame, but our considerations don't reach this level of refinement. Yeah.
If the couplings are all two derivative,
Then there will be
then there's no problem. And if the couplings are higher than two derivatives, they will be suppressed by either string scale or length. So at the two derivative, so as long as every correction to Einstein gravity is suppressed by string scale or length scale, you're done.
Is it not to go wrong if we have many operators for now less than one?
If you had many operators,
If we have not the condition that we should have few operators, if that fails,
yes, few, yes. There, it was mainly a question, for them, it was mainly a question of, like, when you write an EFT, you want to have somehow a finite number of fields. So for them, it was just that statement. For us, we'll be able to be a bit more quantitative. So if you have n matters of n species of fields, there'll be a notion that the higher spin scale is less than n Planck over square root of n. So let's call it maybe not n fields. So there's a notion of the species scale that if you have a lot of fields, it lowers your cutoff.
and this we just get from top down.
Yeah, we'll see that there's inconsistency with the scattering. Yeah, we'll see directly just from thinking about scattering gravitons. Yeah. All right. So before we get this to gravity, let's discuss how we use this equation that is, you all remember, with the Legend polynomials. And let's try to do it we'll do this in the simplest model, just for a scalar EFT, just to understand, get some intuition about how it works. So we have a one-like scalar. It could be phi. It could have a small mass, but let's take it to be massless. It's not going to matter as long as it's much lighter than the cutoff. And unknown physics. Unknown physics at energies greater than some cutoff that we call capital M. So that's the scale of new physics. So we have the scalar and we have the scale M. And we're going to take M phi to 0. And we assume there's no other states at low energy, it's just that scalar. And the question is, yeah, what can we say about the energy, what can we say about the effect of this Abbe scale on the light physics, assuming that even here, unitarity and causality are preserved at all energies. Plus causality preserved at all scale. Okay. So that's the simplest setup. Maybe I can say a few words here because when you describe this sort of assumption to someone who does like lattice field theory, they like don't get it. Because like if you think that the world is a lattice, then like this notion of scattering above your cutoff makes no sense. there's a limit on the momentum you can even use on your lattice. But the picture here is that if we're assuming relativity, this notion of relativity, so the world is not a lattice. And on the contrary, like if you imagine some notion of Lorentz invariance, you can imagine some spaceship that's moving very close to the speed of light, and inside the spaceship someone is accelerating a particle, and some spaceship going the other way. So that way you can prepare scattering processes whose energy is much larger than whatever each of them can prepare separately. So in a theory that has relativity, scattering can be defined up to arbitrary high energies. Okay, whatever does not close the universe, which is okay, it's like way beyond the scale. Okay, so that's why it makes sense to assume that. And then we don't like, even if we cannot describe, even if we not have a theory for what the scattering process gives, the probability that it gives two particles out must be between 0 and 1. And we're just going to use that basic statement. Okay?
So just to make sure, causality was used because you said commutator was 0, and
Yeah.
unitarity was used because of this imaginary part.
Positive, exactly, yeah. Yeah, so we also need to assume, so the other thing we need to assume for the statement of causality is that there's no intrinsic resolution on the time that people can measure. So, but again, using this boost argument, there's nothing that prevents you from measuring time events that are less than the Planck length in the lab frame using boosted observers. So using the time dilation factor, the people in the rockets will be able to test the commutators very precisely. Okay, so we're imagining this exotic tough experiments. Okay, but that's why it makes sense in the theory of that is relativistic and unitary to really impose these axioms all the way to infinity. Yeah.
And the analyticity of that function is like a separate assumption, or it's like?
Yeah, it is the statement of causality.
Oh, that's how you're free.
Yeah. Exactly. Somehow the Fourier if it's causal in time domain, the Fourier transform will be analytic in the upper half plane. It's that type of argument. Great. So the way we approach this model is you could write down some effective Lagrangian. I will skip the effective Lagrangian because the only thing that will matter is like the 2-to-2 amplitude. And let's assume the like scalar is weakly interacting with itself.
Are we in flat space or AdS?
A in flat space. In RD-1, comma 1. Great, thanks. Exactly, so today we're back to flat space. So if you think about this 2-to-2 amplitude, well, okay, if the scalar field is weakly coupled, the only thing you can write down are like exchange diagrams. And it'd be something like some coupling, G square, 1 over M square minus S, plus M square minus T minus some variable. I'm going to drop the masses, so it's just 1 over minus T minus S, plus 1 over minus T, plus 1 over minus U. You could add derivative on the vertices, but once they turn into minus M variables, you won't actually get anything different from this. So then the next thing you can get is like a 4-point interaction, minus lambda. And then you could have, imagine local, and the thing that will really make your EFT an EFT is that you have higher derivative correction at the vertex. Each derivative of the field gives you some momentum, power of the momentum in the scattering amplitude. So we can write minus polynomial in S, T, and U. Okay? And there's a constraint that S plus T plus U is equal to 0, massless particles. Okay? So basically, to classify the EFTs, we have to describe this polynomial a little bit more. And okay, in this momentum space, it's relatively straightforward. Yeah.
Going back to what you were saying about the EFT must break down there at that
Yes.
scale.
Yeah.
So by that EFT, you mean the low energy theory before you encountered that particle, or even including that particle?
Including that particle, yeah. Yeah, you cannot treat this new particle in a field framework, yeah. Yeah, okay. So we have this polynomial. So in order to be more quantitative,
But if you had infinite number of particles, you could, like string field theory is that kind of EFT.
yeah, exactly. So I would say that field theory does not fit in this framework of gravity coupled to QFT. There's going to be a precise sense that, for example, if you try to phrase the rules of string field theory, can you interpret them in terms of correlation function of stress tensor in the vacuum, in the Minkowski space? I take it they cannot. But this is something to be clarified. But that's basically the question. Can you interpret string field theory as giving you a set of rules for correlation function of stress tensor that are coupled to gravity?
Correlation functions. Oh, you mean the other stuff is
Yeah. Exactly. So can you think of graviton scattering in string theory as like the graviton listening to the stress tensor of some QFT? And the concern is that this expectation value of a stress tensor that you define from string field theory may not satisfy these commutators and blah blah that you would expect for QFT.
Yeah, in some sense, we already know, right, that when we have 3 particles scattering with 2 gravitons producing a higher string state, it's not through the stress tensor of that higher string state that
Yeah. Yeah.
So that's the question.
Exactly. So at the zeroth order, the rules of string theory don't look like that.
Sorry, by the T that you wrote, I was thinking that was the CFT correlation function.
Or QFT. Yeah, this will be in the QFT in the bulk. Yeah, yeah,
Oh.
a bulk QFT.
But the other statements about TT being large and all that was CFT, right?
Yeah, exactly. So this board is a bit subtle because here I'm making a statement that deliberately applies to both QFT, to both CFTs to both gravity in AdS and gravity in flat space. But just the meaning of state and so on changes slightly. But this general statement is supposed to hold in any theory of gravity. Yeah. It's basically a local statement. Doesn't matter so much what the asymptotics are. Yeah. Thanks. Yeah. So when you enumerate these polynomials, okay, here I have a single scalar. So the polynomial must be invariant under all the symmetries of ST and U, not just permutation of both symmetry of the particle. And the first polynomial you could write down as a constant. We already wrote it. The next polynomial is linear, but because S plus T plus U equals 0, this vanishes upon symmetrization. So the first polynomial you can actually write down that is non-trivial is something I would call G2 times S squared plus T squared plus U squared. Sum of squares, definitely not 0. Then you can keep going, G3. And actually, it's not, okay, it turns out this exact, I will really go fast on this, but I think if you want more details of what I will write, a lot of this is reviewed in it's discussed in a paper of myself and Vincent van Drong in 2020 on extremal effective theories. So next thing you can write down is, the next order, turns out there's only one thing, is proportional to S cubed plus T. So you could have thought that S cubed plus T cubed plus U cubed was reasonable. It is, but it's actually the same thing as that. So it's the same. So we'll just write one of this, so there's only one thing. And then it turns out that everything else you can write down is a product of these two quantities. So that's a statement about basically symmetrical functions and symmetrical polynomials in 3 variables in mathematics. You can enumerate those, and the next thing is proportional to, yeah, so we did not invent this. And I don't know, I mean, we got this from your paper, but it's probably order, yeah, exactly, right, so. So G4 A squared, G5 AB, then you have a G6 A cube. You can also have a G6 prime A B square, and dot, dot, dot. So I'm using the subscript that denotes the power of -m variables. Just so
Is it
again.
related to that the symmetric polynomial can write as a Schur polynomial?
Yeah, I guess that's a defining statement of the theory of symmetrical polynomials. Yeah, the thing that helps here is that S plus T plus U equal to 0. Otherwise, you will have also the ring of symmetrical polynomials will be generated by A, B, and C. Yeah. Great. So basically, the basic goal now is to understand what we can say about these G's here using this dispersion relation that is now disappeared. Okay? And so if this does not go up, I will just erase.
It goes down.
That's true. Yes. All right. So. Okay. So, and I can also take this one down. So if I take this, I will bring back this equation for you to see. So when you take this equation at the top and you evaluate it on both sides. So here the idea is that this parameterization here, this is the EFT parameterization. It's only valid at low energies. So use it on the left of this equation. Use it on this arc, which gives you the left. And on the right, we know nothing except symmetries. So we use these partial waves on the right. But the EFT does not apply here. And then what you get, what this equation gives you, so if you take the first case, k equal 2, you get some notion that G, so basically it extracts, the contour integral extracts the quotient of S square, which is G2. I'm going to work modulo 2, well, in units where 2 is equal to 1. Okay, so don't pay attention too much to the normalization. Then you get G3p squared, G4p4, and you get an infinite series of term. And on the right-hand side, you get the sum of all the states and their spin, m squared to infinity, ds over s cube. And you get this positive thing times a Legendre polynomial of 1 minus 2p squared over s. This is kind of like a positive measure. We don't know anything about it, so I'm just going to abbreviate it as a measure because this really, yeah, just know that it's positive, so it makes sense to abbreviate it like this. And it's the average of this, minus 2p squared. So p squared is the same on both sides, and s is the variable that is integrated over. Okay, and maybe just for dimension analysis, G2 has units of 1 over mass to the 4th, so we're going to put the s squared here. We're going to take s squared out of that to put it explicitly. Okay?
P squared is like t, or minus t.
Yeah. Great. And here, right, of course, there's a naive expectation here, right? So we expect each g to be of order 1 over some cutoff scale to the 2k, just from dimension analysis. Okay, so part of the game here will be to try to see if we do get the scaling and what else can we say about these g's. Okay?
Maximum. How do you write the left-hand condition usually?
How can?
How it is coming, from where it is coming?
Yeah, so what we do here is this left-hand side here. Okay, so we're doing this contour integral, which is basically extracting the coefficient of s squared in the low energy theory. So in fact, here what happens is, so we're supposed to fix t. So this is s squared plus p minus s4 plus p4 plus something like s minus p squared squared. And if you expand this, so this is s squared. So if you expand this, you see this 2s squared. So this, I should write a 2 here. And then the next term will come from, you see here, there's a cross term. Well, sorry, there's nothing that goes faster than s squared. But this term here is going to have an s squared p squared term. And that gives the G3.
Well, suppose, are you assuming lambda is small? What about loops, two particle loops?
Yeah, we get to that later. But neglect small so far. So the simplest setup, this will be small for the moment. Yeah, when you add loops, things change a little bit. So, but basically, the bound will be corrected by order lambda. So you can do loop expansions of the bound.
But lambda can't be 1.
Now, if it's 1, then but then you can use other techniques, not the one I'm going to talk about.
Okay.
You have to do what people call the primal bootstrap, where you, because here we're trying to not do two things at the same time, right? If lambda is ordered to 1, you have to do two things at the same time. A, you have to bootstrap the interactions between the theory and itself, and B, you have to bootstrap the effect of every states on it. And here I'm just trying to do one thing at a time.
So the theory itself is weakly coupled.
Yeah, exactly. Just so we can really focus on the effects of the UV and the IR.
It's a matter of finding what the theory is, not doing its dynamics.
Yeah, exactly. But there are other techniques that allow you to do that other part. Yeah.
If phi is a massive particle, then all these quantum effects will appear at a higher scale, right?
No, there will be massless cuts. Yeah, if the mass is 0, then.
No, I mean massive. I meant the massive. Phi is massive particle.
Okay. Yes.
Then the EFT is still valid, but you don't
Yeah.
want to take the scale down to the
Yeah.
phi.
Yeah, I mean, even if m is non-zero, we don't want to just do a Taylor expansion around 0. We really want to make sure our expansion is valid up to here. Yeah, we don't want to do a Taylor expansion that would just be valid here. All right. So how do we manipulate this equation? So there are two issues. One of the issues is that there's infinitely many couplings, and we like to bound just one. That's annoying. And the other issue is that this is an average of something that's non-positive. Okay. So let me handle the second, there's a nice solution to the second issue. So let me handle this first, and then we'll discuss the first one. So I'm trying to go directly to I'm trying to skip the history of how this was developed and just go to the end result, which is nice. So the simplest way to deal with this non-positivity, the simplest and clean way to do it, is just integrate against some wave packet. And if you take this equation, and in any case, we have to integrate against a wave packet to make sure this all makes sense. So if you integrate this against a wave packet, so we do this on both sides. And then the claim is that you can find wave packets for which this will be always positive for all possible states on the right. Okay?
For every j, basically.
Yeah, exactly. Each j and s. Yeah. So yeah. So then the problem is to find psi so that the integral of p psi times pj of dot 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 is positive for all s greater than n square and all j, all possible every state. So if you can find such a function, such a wave function, then at least you know something about the sign of the right-hand side, which was the only thing we knew about these unknowns. So we're not going to learn anything if we don't find such wave functions. And initially what we did is we played a game where we...
This will work for all positive linear combinations of Legendre polynomials.
Well, here there's just one. It's just to be true for any single one of them.
Any single, but if I was interested in two, I
Oh, yeah.
positive linear combinations.
Yeah, if you have a more complicated process where you have different channels, different types of particles, it will have to be positive on all your unknowns. Yeah. Great. And yeah.
So on the left hand side after this integration, how it is sure that it will be a positive, like?
Yeah. So if you find such a thing, then we get some inequality on the left hand side, which is still not very useful because it has infinitely many unknowns. Okay, so let's ignore that for a moment. So now I'm just doing something on the right. Okay, and it turns out that it's surprisingly easy to find this positive functional. So one example is if you take psi is equal to 1 minus p over m square. You just compute this integral numerically. I encourage you, just plug this in, compute the integral, and plot it. It's just always positive. It's amazing. It's surprisingly simple to find these functions, and they exist. And another example is the same times p square. So you can find you can find this, and you can multiply this by say alpha. Sorry, let's put it like this: times 1 plus alpha p square. And if alpha is in some range, this will be positive.
So I can translate this into theta, just the scattering angle theta. Right?
Yeah.
So p by m squared is like cos theta?
This is cos theta.
Oh, that is cos theta.
P over m is just, so what's the purpose of this p over m? Is because integrating up to m. So if the cutoff is too sharp, the transform, it's like a Fourier transform, it will oscillate. So you need to put a 0 at the endpoint of integration in order to damp the oscillations and have a chance of being positive. And you do the simplest thing that has a chance of being positive, and it's positive. You can also put cube here. You can put a lot of variance here. There's a lot of things that work. So these options are used in the recent paper by Pomarol and friends. But yeah, the basic idea is that you can actually do analytics. So initially, we played this game by making a giant polynomial ansatz and asking the computer to find combination with the right properties. But you can actually write down analytically a lot of functions that have the right properties. So
Excellent. But is this the same as the question? I want a function of theta that integrates against every Legendre polynomial and gives me a positive number.
yes.
Okay. And so in theta, that will be something funny, but okay. It's fun.
Yeah, because if you rescale p, yeah, p square is a bit of a proxy for theta, but it's not quite the same. Yeah.
You got it.
Yeah. Great, but you need s also to scale. But, yeah. So the message here is that just such wave functions exist. Okay, and you can write some of them analytically. when you can, right. What you do is you make some simple guess and you just plot and see where the issue is. So what is that good for? So now we need to address the other problem here. And something that was done historically in this business, and I'm partly guilty of this, which is that you can try to expand in the forward limit. Because if you do a Taylor, if you're allowed to do a Taylor expansion around p goes to 0, this looks very simple to extract the quotient you want, right? So I'm not going to do that today, but that was done a lot, and that will isolate coefficients, and it's a so-called forward limit. But it's actually not a very great idea. Part of why it's a bad idea is that, let's think about this coefficient here. So we're talking about the imaginary part of, let me draw a graph here, of the S plane and say the p square plane. Okay. So the energy is I. So we're thinking I energies, but we're thinking about small momentum. Right. If we're thinking about I energy and large momentum, we would clearly be doing UV physics. But in this corner, with I energy and small momentum, is that UV or is that IR? And okay, it's not obvious, right? Because it's a small momentum. And we can, okay, this is actually one place where we can get guidance from experiments. You can ask the analysis question in QCD. So in QCD, suppose you have S equal to 1 TeV and P perp equal to 100 MeV. You can do scattering in this kinematics. It's like very forward, but people actually have these detectors at angle of 10 to the minus 5 in the forward directions. They can actually see these processes. That would be probably 10 to the minus 4 or something, but yeah, you have tiny angles, people measure those. Is this described by perturbation theory? And what we know is actually no. The theory of these forward scattering processes is actually controlled by alpha strong at the scale p perp, not S. So the IR, the transverse momentum sets the scale. So this region actually is IR sensitive.
It would be the same in gravity.
The same, yeah, exactly. The same gravity, so you have a long range forces, and so this whole region here is IR sensitive. So if you try to probe Wilson coefficients, EFT coefficients using that region, then everything gets tangled up in the question of the interactions and your low energy physics, and once you have loops, everything gets complicated. So this is like trying to solve the IR of the theory, but actually it's IR sensitive, but it's still a hard question because it has both an IR and a UV scale. Forward scattering is hard to understand analytically. So this this is not a region where we understand so much in field theory. So basically we don't want to be sensitive to that region.
In gravity it would be pure IR.
At long distances, yes, it will be pure IR. Yeah. But still, if you can avoid this region, it makes your life much easier. Yeah.
Very basic question. How can the massless particle be in that region if the momentum is low and still have high energy? How can it happen with the massless particle?
Yeah, the sort of basic process that happened here is that the reason it's non-perturbative in QCD is that you imagine you're doing this high energy scattering of protons, and you can have like a pion in the wave function of one proton that hits against a pion in the wave function of the other proton. And if they hit, that's going to mess up your proton, and it will not come out as a proton. So you have all these processes, and you see that you somehow need to understand the wave function of the proton in order to calculate those processes.
So was your question, if there's a particle exchange and that particle is massless, how is it people? Say your question.
So, okay, my question is, for the massless particle, how can
massless external particle or internal?
External.
massless external, yeah.
So you have two gravitons,
Uh-huh.
virtual particle exchange with some
Yeah.
people. What's the issue?
Yeah, what's the issue? Yeah, maybe you can describe it. Yeah. But yeah, it doesn't matter so much at this high energy regime. It doesn't matter so much whether the proton is massive or massless. And the basic point is that for example, this process, if you Taylor expand around p equal to 0, it will be, you get something like m s p square goes like s to the minus alpha prime p square, something like this. And times some coefficient that depends on p square. And the basic issue is that this will have a series in p square over m pi square plus dot dot dot. So if you when you Taylor expand around small p, your Taylor expansion is controlled by the IR scale instead of being controlled by the UV scale that you're trying to probe. So in order to extract any useful EFT bounds from this region, you have to understand the physics that cancels this, and basically you should just do a fixed angular scattering. Okay? So there's a nice way to do this now, which actually has been developed by Aninda Sinha, and I think it was back then a student, Zahed, and it goes under the name of crossing symmetric dispersion relation. It completely avoids this, it very nicely avoids this issue of Taylor expansion around p goes to 0. And I will just describe it in a crash course on it. So the idea is that instead of fixing t, we fixed a quantity which is called 1 over s plus 1 over t plus 1 over u. We're going to fix that to equal to minus 1 over p square. Okay. And somehow it symmetrically treats all channels. This is why it's called crossing symmetric. Maybe there's one thing I should have said about the other method. So Taylor expansion allows you to isolate some couplings. But to really get mileage out of this, what you need to do is be able to write down different dispersion relations that probe the same information. And you do this effectively by using all channels. So the crossing symmetric relation does that automatically for you because it treats symmetrically all channels. So when you fix this p square, there will be contribution from all the possible channels of the process. So it automatically puts in the right constraint of different channels. And there's a very nice mathematics of it that we're not write down. So one thing you can write down is you can parameterize S as a function of p square and a variable z. And it's going to be something like 3p square times z over z minus zeta, z minus zeta inverse, where zeta is a root of unity, third root of unity. And t and u is the same with rotated z goes to z zeta. So basically, there's a nice picture that in the complex z-plane, which is your dynamical variable, you have 3 rigid limit. So it's like a fixed t where s and u go to infinity. And here you have fixed u where s and t goes to infinity. And here you would have fixed s. So it somehow unites all of the channels with some branch cut on the unit disk. And so it's very nice. So you can do, instead of doing contour integral in S, you do contour integral in the Z variable. And the nice thing is that if you take, for example, the limit here at fixed t and SU large, the physics of this limit is actually exactly the same as before. So when S and U are large, this is the same as t is equal to minus p square. So at high energy, it is exactly the same as a fixed t dispersion relation. So all of the questions about convergence and so on work exactly the same way as in the fixed t dispersion relation. But it's just that somehow in the lower energies that order p square, you're somehow uniting our channels. Okay? So it's very nice. And let me just explain the sort of results you get from this. So when you apply the same contour integration business with this variable fixed, and you integrate over the free variable, either s or z, you get, instead of the average of Lejeune polynomial that we had before, now we get a very similar average, but instead of s, it's a square root. You have to solve a quadratic equation, s minus 3 p square, s plus p square, something like this. And I have the exact formula that I can write, something like 2s plus 3p square over s cubed times this. And the average here is over, again, state above the cutoff. And now the important thing is that you don't need a lot of space to write the left-hand side. Because of this thing is using our channels, it managed to isolate everything except for two coupling. So this is exact plus order loops. Okay? But even the loop corrections are stable, you can be calculable. And that is very nice. So it isolates a finite number of coupling for you. And now the idea is that you have to find a wave function, again, such that the integral over the right-hand side is positive. So find psi so that integral of the right-hand side against psi p is positive for all s and j above your cutoff. For all
to get the other couplings, you would get expectation values of other things?
Exactly. So there's an infinite family of these sum rules. I wrote the first one. But if you keep going, you can extract the other ones. But you see that you get to pick an infinite number of wave functions which extract the same two couplings. So by playing with different wave functions, you can prove different bounds on these couplings. Okay? And for example, so if you find such a wave function which is positive on the right-hand side, then you've proven that a plus ag2, you get an inequality of the form some number times g2 plus some number times g3 is positive. Because the right-hand side is a positive sum, and this number a is basically the integral of p dp psi of p. So just the first moment of this wave function, and this guy is a p weighted by p squared. So you get an inequality like this. And as I described, it's relatively easy to come up with wave functions that are positive. And you can find such things such that you get either sign of g3 and positive on g2. So what this implies, and the typical scale in this psi function, in this wave function, goes up to m. So p is order m in these inequalities. So here there's a dimensionless number times m squared. So what you get are things like g3 less than g2 over m squared times some number, which is not the same as these numbers. We call it number prime prime, and the lower bound on the right-hand side. So you get two-sided bounds of this type, which tell you that basically the ratio of g3 over g2 satisfies the dimensional analysis scaling that you were expecting. And now at some point I will actually need an eraser. Right, so I probably have more space here.
Let me just get it.
Sorry, in getting this dispersion relation, you've assumed something about the arc at infinity.
Yes.
Where is that? What is the assumption? Where has that gone?
Yeah. It has to do with this power of s that you can get downstairs. And it has to do with the left-hand side. I could only extract things that go like s squared or faster.
So lambda was not extracted.
Exactly.
But you said you will show it from this arguments directly as opposed to just using it as a...
Yeah, we can do this without using CFTs. So I guess that will be my next topic, but let me summarize the lesson from this so far. Okay? So by extending the simplest model of an EFT, this single scalar EFT, basically what we showed, maybe I can be more economical in space. The board starts here. Yeah. So what you can show, what you learn here is that basically you get two-sided bounds on all the couplings. So you get two-sided bounds on all couplings. So basically you can make something dimensionless that is gk times m2k is less than some number times g2 m4 less than some other number times g2 m4. Okay, different numbers on both sides. So you get two-sided bound on each thing, which show that in a theory that is relative, if the UV physics is relativistic and unitary, dimensionality scaling is not just a squiggly expectation, it's a theorem. It's a sharp theorem with sharp bounds. Okay? So dimensionality scaling, so a sharp, a sharp version of dimensionality scaling.
And M is the first location of the first singularity of this scattering amplitude.
Yeah, exactly. It's the first UV state. Yeah, it's where this integral started of dimensional analysis. Okay. And you can also try to show bounds on G2 itself, but the issue is that this bound, the upper bound on G2 gets saturated by, it's more like a moral bound that G2 is less than 1 over M4. It's more like a strong coupling bound. When G2 gets that large, the physics gets strongly coupled with the cutoff, and then our calculation breaks down. So it's more like, we know that something breaks down then, but we cannot be more precise than a squiggly.
How we go from G3 to GK?
So for this you need other sum rules. So here I did the simplest, which extract S cube. But there will be an analog sum rule which have a G4 plus something else, and on the right hand side there will be a S5 and so on.
Okay, in that integral you have to put k equal to something.
Exactly. So it gets back to the k in that integral. And for different k's you get this. And actually a lot of this dimensional scaling you can somehow see, it's especially obvious for some of the couplings. For example, this G4 would be given by a similar integral as G2, but with extra powers of S downstairs. So we get the same unknown divided by more powers of a quantity which is bigger than m. So the scaling is somehow, it's very easy to see that you get if you get bounds, they will have the scaling.
Suppose I do a one-loop calculation, so
Yes.
the bound will become much more smaller?
It does become a bit smaller. The other thing that happens is that, okay, the first thing that is obvious is that then you will be bounding the couplings defined at the cutoff scale in some scheme. So you have to interpret what you're doing a bit more delicately. And yeah, people are studying that, and they get slightly weaker bound, but effectively it's correction to the bound. Yeah. So this method is stable, and this was not possible before. When people were thinking about expanding on the forward limit, it was not stable at all against loops. The Taylor expansion was very singular. You get 0 over 0. It was a pain. But when people moved away from this Taylor expansion approach, it's very clear how to treat loops.
So is there any way to make this bound smaller, much smaller?
I think you have to make more physical assumptions.
Okay.
Yeah. Yeah, just in terms of unitarity and causality, I think you get what you get. Yeah. So what you do in practice is you put many of these constraints on the computer. So you see that you have a lot of choice of wave functions that you could choose. But here also, even if you're just interested in G2 and G3, you could use that, but integrate against wave function that kill all these terms. We call those null constraints, some identities. So by combining more and more of these equations, you can get sharper and sharper bounds. But numerically, it converges. Great. Okay. That's what I wanted to say here.
Usually when we think about EFT, this similar like squiggly thing,
Yeah.
we think that there's really an order 1 coefficient, right?
Yeah.
Here, your thing would be consistent even if GK was like much smaller than there was,
Yeah,
it can't be stronger than this.
No, exactly,
It
but
can be much weaker.
exactly. So the physical picture, the mental model you can have is that you could be exchanging some AV particle like this, and if your coupling to the AV particle is small, then the overall scale of everything will be small, but the pattern of terms, like this is g square over m square, like 1 plus s over m square plus dot dot dot. The pattern of terms will be controlled by the scale m, but the overall coefficient is a free parameter. I don't know if that's what you were alluding to.
No, but I meant like, if that's a model for what could be happening, but since you just proved the bound, there could exist a theory where this thing was not controlled.
No, exactly. So it will not look like this model, but these bounds still show that the thing will still look like some Taylor expansion that converge.
Yeah, I just mean that it's showing that the effect can't be stronger than this, but it could be much weaker, right? Like it could be coefficients which are much smaller, say controlled by some larger scale m.
Yes, exactly. It could be that new physics come at the scale 10m, and then the pattern will be then you'll be far from saturating these bounds.
Yeah.
Good. Okay. So. So I wanted to say a few words about, but I think, if you want to jump into this business, I think you should start with the modern approach, which is this crossing symmetric approach, Okay. So I guess Shiraz asked, Abhijit asked me to justify this from S-matrix logic, so let's get into that. I will be a bit quick here, but I just want to get the idea across. So how do we justify this from S-matrix side? From the S-matrix side. So the starting point would be.
Sorry, a big question. The size at the moment are just some mathematical trick. It's these wave functions that you multiply. Is that a physical?
Thank you. Yes. So so why is it better to use this wave function as opposed to like forward limit? But the basic point is that we're trying to probe physics at the cutoff scale. We're trying to prove the EFT at its cutoff, the coefficients there. So the best way to do this is to actually focus on impact parameters that have ordered that scale. So the point in life of this wave packet, so for example, one thing you can do is you can look at this wave packet that gives you positive and blah, blah, blah. And one thing you can do is you can Fourier transform this wave packet and ask what does in B space, what did they look like? And in B space, these wave packets will be positive. And they will typically be dominated by inverse of the cutoff scale. So basically, we're doing scattering as focused as possible if we want to probe the energy M.
But suppose I change the shape a little bit, it will no longer be positive. Would you be able to, say that it's not positive because this feature has been compiled? I was wondering whether the positivity of the wave function is a simple physical determinant.
Yeah, I think positivity in B space, it's a good question. I'm not sure. We really want to probe a positive combination of the amplitude somehow, but just mathematics. It's a bit of a strange. I think in the one dimension, mathematicians have some theorems about the space of functions. So the space of function that matters if they have compact support in momentum space and are positive in impact parameter space. So such functions exist, but the space of some such function is not, I think in one dimension mathematicians can analytically solve it, but in higher dimension I'm not aware of any result. They exist certainly, but and we can explore that space numerically. Okay. So I try to justify the boundedness and so on using arguments that are very similar to CFT arguments from yesterday. So we think, so this is time going up. and we're doing this, this scattering. And the idea is we put some wave packet here. So let me draw some wave packet. And we're trying to scatter this wave packet, and you want to use that the commutator vanishes space-like. So it should not arrive the other side faster than light. So we want to take an expectation value of a commutator of, this is 1, 2, 3, 4. We want to take a commutator of phi 2 and phi 3 in the state 1 sandwich between 1 and 4. We could also put it here. 1 in, 4 out. We want to use that this is equal to 0 space-like. Okay, this is what we're supposed to use. Exactly what we used yesterday. Okay, and we want to use this for scattering in the for the scattering case. The first thing you will notice, I will just make a few general comments. The first thing is that this statement is only useful near the forward direction. Because if you imagine like there's a fixed angle scattering, and particle goes from here, hits something, and then comes back here at some angle. This final measurement point here will be deep in the future light cone of where it started. So this vanishing commutator, you only have a chance of spinning outside the light cone if you're close to the forward direction.
Yeah. Causality could be violated near forward scattering.
Yeah, exactly. But this is where you can test it. If you look at fixed angle scattering, you don't really expect any useful statement. Right. And
that's why J kinematics is important.
Exactly. So this is why Ridgey. Right. So scattering processes only probe causality in Ridgey kinematics. The other thing that I want to quickly explain is that, okay, now we put this wave function. We understand we're doing forward scattering. So the useful variable is to have a function of p perp. And so our state will be labeled by some wave packet of p perp and some, say, large light cone energy that is large. Okay, so that's the large energy going this way. Okay, so we can parameterize a wave packet, our particle in terms of a transverse wave function and some energy. Okay, these are two variables. And the other thing that is important to notice is that, okay, this is P2 minus.
Sorry,
Yeah.
So does this also mean that the right extension of J for higher points is to just scatter these two bunches in the forward limit?
Yeah, that's one. That's exactly. So, no, I mean, you could have a bunch here and a bunch here, and you can define the rigid limit as having a large boost between these bunches, large relative boost. That's it. People also talk about multi-Ridgey. We have a large boost, less boosted, and something going the other way.
But that also probes?
That also not so much. No, it's really just Ridgey. Yeah.
Only the bunching, right?
Yeah.
Look, as long as one guy is going forward, whatever the others are doing, it's in danger of
No, whatever meaning what? Meaning, are you taking their energies to be large or not? I mean, this is equivalent, right? This, if they're kind of not doing much, and they're doing, or they're doing going the other direction fast, they're just boost equivalent.
No, I'm saying, that, let's say 6 particle scattering. So these two could be doing a non-trivial 4 particle scattering. And this guy's almost going forward. But the interaction between these could violate causality. So as long as one guy is almost forward, some interaction of something with that could take it away from him.
Okay.
I don't.
But cool. But the point is that cannot happen.
Yeah.
But we can only really test it for the guy that's going forward.
Yeah,
But it could be a bunch. You could have a bunch affecting some bunch here in principle. Yeah. But
I mean, the other guys cannot do a fixed angle scattering, right?
Yeah.
Why not?
Because the thing that you're probing there would be in the time like.
I'm just probing that this guy can't go outside its light cone. What the others are doing is irrelevant to this.
I think I think I agree that. So if you could have a bunch of spectators that are not going the forward direction, and they would just be spectators in this argument.
I see. So the other guys can do
Do a lot of things.
Yeah, okay. And the other thing that the next point that's important is that it's just a kinematical point that we're talking about the Mandelstam energy S, which is like energy square. But in this limit, this guy is a large P plus. At high energies, S is like P1 plus times P2 minus. S is like P1 plus, P2 minus, is linear in the variable P2 minus, which is conjugate to the time we're trying to probe. Linear in the frequency P2 minus that is conjugate to, let's say this is x plus 2, so x2 plus minus x3 plus, or x3 plus minus x2 plus. Okay? So the fact that the commutator vanishes for this quantity being negative, so the commutator equal to 0 when this less than 0. So the fact that the commutator vanishes when this is negative means that the Fourier transform in the P2 minus plane is analytic in the upper half plane. And because P1 is fixed, that is basically translating into analyticity in the upper half plane. Okay. So immediately, just from this cartoon, we understand why we get analyticity in the S upper half plane. In S upper half plane, at least for S not too small. That's going to depend, when S is of order, the P perp here, these arguments break down, and there could be some region in the middle that we just have to check separately. But the basic argument that you have analyticity in this large S swath of the complex plane is really just the Fourier transform of a function that vanishes.
And that's this function, the function that you wrote here?
That function. Yeah. Okay? And also, the statement that the function vanishes for this time being negative tells you not just that it's analytic, but also tell you that it's not growing exponentially. Okay?
So that position space statement was in the boundary CFT, right? Or should I just think of this as some quantum field theory?
Yeah, okay, here I'm trying to do a S-matrix argument directly.
Okay.
So this phi you can think of as an asymptotic field. You could also think of the off-shell field in LSD formalism. So yeah, you can think of this as a QFT argument about local fields taken to infinity, or some scattering. But it's a statement that can be interpreted directly in terms of scattering. Okay.
And can you say that argument S is equal to is linear in frequency that is conjugate to this?
Yeah, it's just because that when this is large, like on coordinate, there's a P2 this is S is P1 plus P2 square, but the square is a plus times a minus. Yeah. So S is like P1 plus P1 minus times P2 plus P2 minus, and one of these is small and the other is small, so it's just a simple product. Yeah. Great. So that's the logic. Maybe, okay, well, there would be one more step about the boundedness. But before I get to boundedness, let me maybe mention why the axiomatic people think this is not a completely rigorous argument. There's a subtlety, which is why people like Epstein, Glaser, Bro wrote 60-page papers in the 1960s proving crossing and analyticity. And the basic subtlety is that if you think about off-shell fields, this commutator being equal to 0 implies analyticity, space-like, implies analyticity for imaginary part of P2 mu in the forward-like cone, so time-like and positive. Okay, so just statement of Fourier transform with some support. You get an LST for some imaginary part in some cone. And the basic issue is that when you restrict this to on-shell, so this off-shell, everything is clean and simple. When you want to go on-shell, your P2 looks like P2 minus, which is the large coordinate. Then there's P2 perp square over P2 minus, and then P perp. This is small. And there's an issue that if this is in the upper half plane with a plus I epsilon, 1 over this is the wrong sign. And you spill this small quantity, the small one is slightly outside of this domain of analyticity that you get from the off-shell Fourier transform. So the statement that people say is that this axiomatic domain does not intersect the mass shell.
And is that the same statement that here you cannot be having that commutator vanishing and also be scattered in this diagram?
Yeah, if you have some p perp, if you have some small amount of p perp, there'll be some little small angular scattering, and you'll be going more. You're not probing the sharp transition.
I was asking something simple. I'm saying that at the moment these two particles are this vanishes when two particles are outside the light cone.
Yeah.
So this vanishing is really not probing a scattering experiment.
Yeah.
And that's somehow this.
Yeah. So this is subtlety, and people, the solution, mathematicians have found a solution to extend the domain of analyticity and prove that this works in some regime. And actually, there's in this paper, Crossing Beyond Scattering Amplitude, with Sébastien Misera and Offy and Mathieu Giroux a few 2-3 years ago, we really tried to understand physically what's going on with this argument and so on. And actually, there's a very simple picture that we explain, is that, okay, this constraint on P minus, the extension of P minus, basically is the physical argument is that it works if the particles that can propagate inside your diagram are not moving faster than the particles outside. So somehow the slope of P plus versus P minus tell you about the velocity that the particle is moving in, and works if the internal states can't move faster than external states. So that's the somehow criterion that answers that this analyticity work. So somehow if you scatter a massive particle and they can exchange light, you can run into trouble. And actually we have examples where you do run into trouble. But if you scatter massless particles, you should always be fine. So that's the physical argument we made there. Okay. So, all right. Okay. Next thing I have to explain. Okay, there's analyticity in the upper half plane and not so crazy growth.
Sorry. In the CFT, you had a similar, you're looking at this Regge kind of kinematics, which was not quite the scattered kinematics.
Yeah. And
yet you were able to find.
Yeah, there we have to do some funny transform. Here we don't have to do that.
But is there an analog of doing something like that?
I don't see it. No. Somehow this transform has to do with the. Somehow it seemed that this transform was undoing something about the geometry of AdS, which was going from the boundary to the bulk of AdS. But if you start already in the flat region, it seems you don't need it. That's what seems to be the case. The next step is actually very similar to what we discussed yesterday for CFT. So in the complex S-plane, now we explain analyticity in some big circle. And now we have to explain what it connects to on the real axis. Okay. Well, obviously here it's going to be the scattering amplitude. But we have to explain a little bit what it connects to on the left-hand side. And here again, the picture is that asymptotically, this becomes some, phi3 here becomes some creation annihilation operator of out state, because 3 is in the future. And this guy here becomes creation, is a combination of creation and annihilation operator of in states. Okay, and then you can calculate this commutator. And you get two terms. You are in commute with in and out commute with out. So you have a term with in commute with out. And which term you pick depends on where the sign of the energy. So on this positive axis, you're creating something with particle 2. So you have something like a commutator of A3 and A dagger 2 in the state 1, 4. But this commutator, because A3 will not, there's nothing to absorb. This is out, in. There's nothing to absorb. This is basically, you can drop the commutator, and this is the amplitude for 1, 2, go to 3, 4. Okay, as expected. So this commutator, just one term contributes. On the left-hand side, you get a commutator of a dagger 3. Let me put it on the left. So A2 and a dagger 3 times 1. Again, you can drop the commutator because only one term is non-zero. You have to create something before you absorb something else. But now there's a bit of a subtlety in that this is in, out, exactly this OTOC business we had to deal with yesterday. And remember what we did yesterday is we took this in particle and we used this, we shifted it by one Poincaré patch so it became an out particle. And now we can do the exact same thing. We can use stability. It has a different name in S matrix theory, but it's exactly the same thing. What happens when you take a state with only one particle and you evolve it? Nothing. It just stays there. It's a stable particle. So it's the same as 1 out. And we do the same thing for 4. So this quantity is the same as 1 out created 3 out. So basically 1, 3 out times 2, 4 in. So this anti-time order thing, which is exactly the complex conjugate of the amplitude for 1, 3 bar goes to 2 bar 4. Okay? So the thing you left on the right you have an amplitude, and on the left you have a complex conjugate of an amplitude. So the fundamental crossing moves relates those two things. Okay? So these statements are valid on the real axis. And so what do we know so far? Okay. So can you raise? Okay, so we now have an amplitude here, we have an m star here, and we know here we have sub-exponential growth. Otherwise, it will be a problem with it will not be causal. Okay. This is still too weak compared with what we want, because we need to show that the integral over ds over sk plus 1 of m converge on this arc at infinity. So we need to be able to say something about this k. And the sub-exponential growth tells us only that k is less than infinity. Well, yeah, doesn't tell us anything. So what do we have to do? It turns out that once you have this sub-exponential growth, all you need to do is bound this m on the real axis. So if you can bound m on the real axis at positive large S and negative large S, this version is just a complex analysis blah blah that tells you that it's going to be bounded everywhere. Okay. So then we use that on the real axis, this amplitude m. It basically comes from a matrix element of the scattering of the S matrix, which is unitary. And we're scattering a state with a momentum psi p2 perp, p2 plus, and psi p1 perp, c1 minus, and here we have wave function. So what we're going to use is that because it's a unitary matrix, a matrix element of a unitary matrix by Cauchy-Schwarz is less than the norm of the states. Is less than norm. Okay. And what is the norm? If you take this guy, psi, psi, the norm is just a product of things like this. Psi 2, psi 1, psi 1. And what is this thing? This is P2 minus, and this is P1 plus. So basically, we get that the M is less than S times a constant on the real axis. This is after integrating against a wave packet in P perp square. So if you integrate the scattering amplitude against a normalizable wave packet, the transverse direction, it's automatically bounded by this. And then, now we're done. By this complex analysis, blah, blah, I think it has the name of Fragment-Lindelof theorem. You can quote this at the dinner. And this implies that basically M over S greater than a constant in the upper half plane. Outside for maybe some region in the middle that don't necessarily care. But at infinity, at large S, large S. So we get this bound that M over S is bounded by a constant. It's a yeah.
How does that fit with this, whatever, the forward scattering about this S like S?
Yeah, let me get to that.
Right, yeah.
Thanks. Great. So let me give a name. So Shiraz, since Shiraz mentioned the Frossard bound, let me call this the Frossard lemma. Okay, this statement that M over S is bounded by a constant. Okay, I'm going to try to relate this to Frossard bound and other theorems. Okay.
This is better, right?
Sorry.
This is better, right?
It looks better, so, but it involves a wave function, which the Frossard bound does not. So let me contrast them in a second.
Okay.
Okay, so first, let me just conclude this. So the fact that M over S goes to a constant means that integral ds over S square is marginally convergent, divergent. So we need ds over S cube to converge. So this converges for, well, it converges for any k greater than 1, but the first integer that satisfies this is 2. Okay? So
where do you use fixed impact, fixed, that is the Regge limit and not fixed angle?
if you do fixed angle scattering, nothing tells you that you don't have exponential growth.
And what they told me now, that doesn't have
No exponential growth was that, right, so how does it work? So if you have a function whose Fourier transform vanishes for in this causality thing, exactly. So you have a function that vanishes for t less than minus a, then its Fourier transform can grow like exp of ia omega. So exactly. So it's very important that the threshold is at 0. And it's only in the forward direction that it's the sharp threshold is at 0. It's only in the forward direction. Yeah, so it implies convergence of this sum rule for k greater than 1. Okay. Maybe it comes up. Great. So then you contrast this with the Frossard bound. So there's actually two different versions of the Frossard bound. Well, one of them, which is the hard part of it that Martin proved, is the by the way, we can keep going and I'm happy, but I will not be offended if people leave at some point. Okay? Just to be clear, okay? Yeah. So the Frossard bound is this this statement that one of the versions is that if you take, for example, for pion scattering, okay, the details depend on exactly what you scatter. if you the scattering amplitude f of s and t is strictly less than s squared. So this over s squared goes to 0 for fixed t, and some range, I think it's t less than 4 m pi squared or something like this. So there's a statement like this as s to infinity. So that is the usual statement. So the exponent in the Froissart lemma is stronger than the exponent in the Froissart theorem. And the reason we get a stronger exponent is that we're scattering a normalized wave packet and not plane waves. Okay. So yeah. So this holds for plane waves. And the hard part of the theorem is to bound how the physics can spread in the transverse plane, which we avoid by taking wave packets. Okay? So hard. So basically we must bound what François and Martin had to do. They had to bound the Fourier transform of x of I pb times m. Roughly speaking, imagine an amplitude function of energy in impact parameter space. This thing is easy to bound. But bounding the thing which is hard to bound is D2B. So that's why Martin won many prizes for making his proof. Okay?
So the B dependence of your bound
yeah.
is the difficult thing.
Yeah. Exactly. And thankfully, for this EFT business, it does not matter, because the whole point is that we get the strongest possible bound by making B as small as possible. So the physics at large B is completely orthogonal to what we care about for EFTs.
So the previous argument was in the B space, then
Yeah.
now we want to go to T space.
Yeah, well, Froissart, they wanted T space for some reasons.
Yeah.
Yeah. And the other statement of Froissart bound is that the imaginary part of ms at 0 goes less than s log square s. And okay, this we can discuss how it somehow imply by that, but okay, this is the other famous statement that you might want to know. So that's a bound on the cross-section. The total cross-section cannot grow faster than log s. And the constant is 1 over m pi square.
Or is that
Some
just
number.
if there's S all over the place and then the area is set by m pi square?
Yeah. So the strongest possible scattering, basically, that follows from this is an amplitude that go like s to the 2 minus epsilon times e to the 2 m pi b. So the dominant impact parameters that will control are m pi log s. So if you include impact, if you compute this d2b up to m pi 1 over m pi log s, then you get the Froissart bound.
So in B space, if you just put in the fact that it cannot grow faster than S and that it dies off when B is larger than 1 by
Yeah.
S, that translates to that.
Yeah.
Okay.
Great.
And the above argument, where was it clear that we are in the B space?
Yeah, we're not quite in B space. It was just psi, but still physically you can find wave packets that localize you in B. So the Froissart lemma easily get that, at least up to some uncertainty in B. Yeah.
Psi is where any of these positive wave functions.
Yeah. For this argument, they don't have to be positive. They just have to be normalizable.
No, but sorry, I was asking where did we use that these are wave packets and not plane waves?
We used that this was a finite number.
Okay.
So we cannot use Cauchy-Schwarz for plane waves. That is the entire issue. Yeah.
Nicely. And then when we do this chaos bound, we use this Froissart lemma basically, right?
Yeah, exactly. That's all you need. Yeah.
Why then there is no log s issue
Well, this I don't know. There could be log SSU if you do fixed t, but I think let's put it the reverse. So I think one question you can ask is, so Shiraz had these conjectures about classification of gravity theory that satisfy the S square growth, and you both of you had this conjecture together, and yes, of course, yeah, and one question is, yeah, initially this analysis is done at fixed t, and you look at the rate of S growth, but clearly if you Fourier transform to go to fixed b, your conjecture is still basically the same. So I think you can rephrase your conjecture in terms of the Froissart lemma without any loss of implication and content.
Sorry, what is the conjecture?
Yeah, the conjecture, well, there was several of them, but one of them, you can probably describe it yourself, but the one I'm referring to here is the one about theories of gravity that where things don't grow faster than a square, have to be Einstein gravity plus small correction.
So you're saying it's better to phrase it in the wave packet language?
Yeah, I think so. And actually you can ask, you see the key of the proof of the Froissart bound is that the pion is massive. If you don't have a pion mass, you cannot actually prove the Froissart bound. And there's been a nice paper by Zhiboydov and Haring where they ask, given what we know about gravity in the IR, what is the behavior of M at large impact parameter? And they show that it depends on the scaling dimension, the space-time dimension, but in 4 dimensions, the Froissart bound is not valid. The Froissart lemma is, but not the bound.
Why?
It's because so the first thing that happens at large impact parameter in gravity is that you get a large Eikonel phase, and so there's the range of impact parameter where so basically scattering at large, so the radius at which you can scatter grows too fast with energy. Yeah, it's not even because of black hole, just because of Eikonel phase is too large.
But then there is, using the, so presumably when you try to translate this proof of chaos bound by the CFT to scattering,
yeah,
it would naturally be in the wave bracket language.
Exactly. So let me get to this a little bit. Yeah. Yeah.
Shiraz and friends worked on that, right? So that was clear that this distinction is there.
We worked in fixed T.
Fixed
Yeah.
T.
Yeah.
Okay. There's nothing wrong. I think a lot of the discussion transposes to this, but this is the easiest way to justify it.
No, but I thought in fixed T we worry about log S factors and even violation of that, right? In the gravity case and so on. So how is that comparable?
Well, we're looking at S square, no? S log S is well below S square.
No, but that I was thinking of S becoming S log S because of that change. Similarly, S square will also become S square log S because of that change. Because of, you would use the same complex analysis fragment in velocity, right? With the
In CFT, S square is a bound, right? Telling the chaos bound.
Yeah.
in CFT, yes, but now the question is when it translates into scattering, it is a bound at fixed wave packet, in the wave packet language or fixed T.
Fixed
It
wave
could
packet.
be that in
Yeah,
fixed
exactly.
T you
Yeah.
might get
So the CFT correlator naturally maps the thing with wave packets.
Yeah. No, but that's why I was asking.
Mm-hmm. Yeah.
So maybe I would have to
Okay.
Actually, it was in angle space. So maybe with that small t. So
Okay. Okay. Yeah, fixed angle, I'm not sure we can say much from causality. But let me comment briefly for the benefit of everyone on how this relates to the bound of chaos and all these things. So the idea is the following. So now that we explained that this vanishes, well, this where S is bounded like constant at S goes to infinity and in the direction, we can use this to write down some dispersion relation. So we can write basically that if you take integral of ds over S minus, I'm just going to do a random argument, S0 cube. Let's say I choose a point S0 here. and I start with a arc like this, a little circle. So that gives m prime prime of S0. We can express m as a contour integral like this. Now we can deform this contour and add into something that looks like this. This is 0, I drop, because I had cube, which is big enough. And let me add, for good measure, 0 in the form of an integral below. So we have this on this integral becomes the integral of the imaginary part of m along this real axis. And maybe you have to do a little bump here in the low energy region, but that's going to be a fixed region. We're not going to care about this.
Sorry, Simon, just one thing that I probably missed there. So this negative real axis, what happened? That also turned out to be a different scattering only, so you can use physical arguments to...
Yeah, it's a different scattering, but it's still bounded in the same way.
Same.
Yeah, but in order to really use this complex analysis, I really need a bound on both.
Yeah, that's why I
Yeah, so it's very important that the negative axis is important, is physical.
Okay.
And for example, that's what would go wrong if you do fixed angle scattering. Now, if you fix angular momentum, then it's physical on the right, but you get a left cut that's not physical, and you cannot bound it. So fixed angle scattering, the left cut kills you. Great. So you have something like this. And it's integral over the whole real axis, and this whole thing here is positive. Well, yeah, S, yeah. Okay. So I think, yeah, imaginary part is positive on the right, and on the left it is the other sign, and it's yeah. So it managed to be positive. So the basic point is that what you can see from this is, okay, I think I didn't prepare this argument very well. Okay, a basic fact is that you see that if there is some range of S where you can say that m goes like S square, the coefficient of S square will be positive. Okay? If m goes like some coefficient times S square, then C is positive. Okay? Because that it's an integral of something positive. Okay? So that's one thing. And this argument worked best. Yeah, I think I won't be able to explain it very well. I want to say something about the rate of growth. Let me make sure I get it straight before I say it. Okay, I think I'm not going to be able to share it. So there's an argument. It's in my paper. It's in my paper on analyticity in spin, that says that by manipulating this equation, you can basically show that if you write S0 equal x plus iy, you go in the complex direction. You can show that y dy of log m is between 0 and 2. Which means that if the amplitude looks like a power of S in some range, that power must be between 0 and 2. Okay? And this argument is essentially the same as an argument that's in the appendix of the bound of chaos. So it's referred to as the chaos bound. So if you have some transient regime where the amplitude looks like a power law, this power cannot be too fast. And yeah, that is a very important constraint on modification of gravity.
And no extra physical thing enters, right?
No, exactly. Well, as soon as you have that and analyticity, it follows. Yeah. Yeah, as soon as you have this boundedness and analyticity, it follows.
Yeah, the appendix argument you were talking about was just like causality.
Yeah.
Causality was divided.
Yeah. Yeah. Maybe I can mention also something. Okay. I think it's getting, we keep going, but I think in the interest of time, maybe we'll not discuss everything. Maybe I would postpone to tomorrow a more detailed discussion of gravity. But maybe one thing I want to say about this is that there's basically these different regimes where people can make arguments. So what we're going to do with this in gravity is that we're going to apply this to graviton-graviton scattering. And we're going to be thinking about the regime with S much less than m Planck square, so that the physics is weakly coupled. And yeah, we're going to be applying to this region where basically the three-level exchange will dominate. And I just want to contrast this with other argument that people have used in other contexts. So for example, there are famous discussion of C and Z and other people who basically argued that if you fix the impact parameter B and you take S very large, this amplitude should exponentiate. And if you exponentiate the 3 amplitude, which is that m of S bigger than m Planck square and B, in gravity it's natural to expect it to exponentiate of 3s. And that thing here goes like IS times some function of B. So the S square growth, like so yeah, I can probably just say one more thing here. So an MST for gravity goes like g Newton S square over T. But when you go from T space to B space, there's an overall kinematic factor of S that we normally divide by, which is the norm of the state I talked about earlier. So MSB, we say, goes like g Newton S over B to the D minus 4. Okay, so that's that thing here. Okay, so the S square growth that I talk about represents a phase that goes linearly in S if you exponentiate it. And in this context, like if you have a scattering phase that's proportional to S, the coefficient tells you whether you're at time advance or time delay. D phase over ds is equal to basically 1 over the passive P1 plus times time delay. And if you don't want to have a time advance, you need to have delta positive for all B. Right, so, and then they analyze this three-level amplitude and discuss constraints in the theory from requiring that this time delay is positive. Here we're working in a different regime. We're working in a regime where we don't need to exponentiate, but that means also that this time delay is not macroscopic. It's like h bar or something. The amplitude is small, but in this regime, assuming that the UV completion respects causality and unitarity, we still get the same conclusion about the sign of it. So here we get that here we get the same conclusion that delta has to be positive, but from a completely different argument that operates in a different kinematic range.
CEMZ also, because at least most naively they worked with non-zero impact parameter.
Yeah.
Didn't constrain contact terms.
Exactly, but this argument constrained contacts also.
Yeah.
Yeah. Okay. Yeah. So maybe since this will set the stage for tomorrow, maybe I can review here the CMZ argument, because now that everything is set up, it's almost done. Yeah. Just a kinematic, it's just a definition if you wish, but MSB is defined to be 1 over S times D2B, sorry, D2P perp X by PB.
When you have bounded MSB by S,
Uh-huh.
right, the MSD got bounded by S log S.
Yeah, but yeah, that is true. But that point, yeah. But we don't have to use this bound. The point is that you can express this as in terms. This is closer to the wave packet thing. So MSB. So let's put it like this: if you integrate MSB against a wave function of B, You can define it like this, but it's the same as integral of psi p times msp, and which is m psi. So you, in order to bound this thing, you really just need the Froissart lemma. And then you have some wave function in B. Yeah. Yeah. So it's important that yeah, you don't need to have an intermediate step where you need to bound an SP. It's always wave packets.
I think Abhijit was asking, at least I was thinking that when you were discussing earlier the connection between what Froissart did and wave packets,
Yeah.
there was something like an MSB, there was something like an MST.
Yeah.
Now, is this extra factor of S the same as the fact that MSB in that discussion was bounded by S, whereas MST was bounded by S squared?
Not S square, S log S.
There were two things, right? One was an S, one was less than S squared, one was.
Yeah. Okay.
There was what he called Froissart theorem and Froissart bound.
Froissart lemma was this S.
S. Then he had Froissart theorem and he had Froissart bound.
No.
Yeah.
No, there is
MST divided by S square is less than S squared. That he had two things on the board.
Yeah.
I saw log square also at some point.
Yeah, that was for the total cross section, imaginary part of it.
Yeah.
But first he had some statement just about MST, not imaginary part.
Yeah, but that was S log S.
No.
No, the MST less than it's less than S. Yeah. MS over S square to go to 0.
Oh, that
For
will,
fixed T.
But isn't Froissart bound S log S?
But at T equals 0. That's for the imaginary part at T equal to 0. But if you want fixed T, it's a different.
Oh, I see.
You don't have the log. At fixed T, you don't have the log.
You have S square.
But you have a weaker power.
Oh, you have S square.
Yeah.
Okay. Okay.
Yeah.
Is
But this is this.
Yeah, I thought that then that's the same as.
Is this the same S or it's just different?
No, I think it's different because the S log S versus S square is the same space. They're both in momentum space. Yeah.
Okay.
It's different.
So this is just some other definition.
Yeah. Exactly. But this definition is sort of forced on you because you want this to be like a phase that's dimensionless, and so you have to make sure you're scattering normalized states. So this is just from the relativistic normalization of states.
Is another way of saying this that if you go to partial waves?
Yeah, exactly. This is the partial wave. Yeah,
Partial wave.
exactly. This is same as what I call.
L by S.
Exactly. This is the same as this partial wave, where B is somehow 2G over square root of S or some standard formula like this. That's, like if you scatter two particles with some impact parameter B, you can ask what's the angular momentum of this. Okay, I forgot where the 2 is, but.
So can I never think about B but only think about partial waves? Is that okay?
Yeah. No. Well, in this argument, yes. But in terms of these wave packets in J are not good because you get a left cut that is not physical. Yeah. Somehow fixing B in this picture, fixing B is friendly to like swapping the two particles, but fixing J is not. Okay. Yeah. So let me just quickly review this argument. So basically, using that this phase shift was positive, they got an interesting conclusion, and that's going to be basically the starting point for these gravity constraints tomorrow, is that you can think of this B. Well, one nice thing first is that this B is positive in inertia and gravity. It's great to get time delays. And the other thing is that in gravity, okay, suppose you fix some scatter here and you scatter against it. You can either scatter plus or minus helicity on both sides. So the scattering phase is really a matrix. And it looks like Gm over B to the d minus 4. It's a matrix. And one cool thing, which is really not trivial, and it's an amazing fact about inertia and gravity, which is inertia and gravity, it's diagonal. And it's actually a proportional to identity. So both polarization and inertia and gravity, they always move at the same speed. So here we have 1 and 1. And this is really deep, because if you think about like causal structures and metrics and so on, like in gravity, you can ask yourself, okay, the graviton has two polarization. Which one defines the causal structure of space-time? But somehow in Einstein gravity, this question does not happen because never appears because the two polarizations move at exactly the same speed. No matter what geometry you throw them in, they move at the same speed. So there's no B refringence. B refren, okay, I'm missing some letters here, in gravity. So there's no ambiguity in what the causal structure is in Einstein gravity. However, once you start adding correction to gravity, like some Riemann square in higher dimension, then if you have a theory that is R plus this over 16 pi g, if you have a theory like this, then you get something off the diagonal. The delicious changes. You get some lambda, and it is dimensionful, so you get some lambda over b square, get some lambda over b square. You get things like this. And now it's weird because you're different depending on, you have two objects, so depending whether you polarize in the plane or out of the plane, you have different speeds. And what this argument shows is that when this ambiguity becomes severe, so when the impact parameter becomes of order lambda, then the eigenvalues of delta violate this causality constraint, and new physics must show up. So if you impose a delta positive, that means that this formula must break down. Must break when b square is less than lambda. So some new physics must appear, and they add some various arguments to classify these new physics. They explain that it has to be a tower of higher spin particles. It could not be just some boring scalar that you add. It had to come from some exotic things of the type that I mentioned at the beginning of the lecture. So part of the game that we try to do here was to try to make, using this dispersion relation arguments, we can turn this squiggly into an actual bound where this becomes, this cutoff becomes the actual mass of these spin-4 particles. So the goal is to make, to be on the road where we make more and more precise what happens at this cutoff. So
this formula must break down to preserve causality.
Exactly, because this formula itself breaks causality. So if you try to go to small impact parameter space, some other correction must appear. And they argued that this instead of exchanging the massless graviton, maybe you exchange, if you exchange some tower of higher spin particle in T-channel, you could resolve this. Yeah. They argue that this can fix it, but nothing else could. Yeah.
And basically, any one higher spin particle will be S to the J, which would make the causality problem more severe.
Exactly. So you need the tower. As soon as you have these guys, you need a tower. You need to be on some kind of rigid trajectory.
And spin 2 will not do because that will just be S squared.
Yeah, it doesn't help. Yeah.
Does every type of modifications of Einstein lead to similar picture?
Yeah, so this is all the modifications that are like higher derivative of this type. There's one modification that is not constrained by this argument. Maybe I should mention it. Because what we call a modification of gravity in this case here is something that really modifies the graviton scattering. On the other hand, in the people doing cosmology or astrophysics sometimes, they talk about things like f of r gravity, with r plus r squared, not Riemann, but r. But this f of r actually is the same as r coupled to a scalar. So some phi with some potential b phi and some particular shape. So from our perspective, this is not a modification of gravity. It's just like a perfectly reasonable gravity coupled to a scalar field. So just a perfectly reasonable QFT. So for us, so the thing we actually constrain by modification to gravity here, I mean specifically a modification to the graviton 2 to 2 amplitude. And this f of r actually does not modify this amplitude at all. Yeah. All right, so I guess we can stop here for today.